This is 4.238. Determine whether the set in R2 with these operations is a vector space. If not, state all axiom that fails. So now we need to check those 10 axioms one by one, and if it satisfies all 10 of them, it is a vector space. If not, even if it fails one, it's not a vector space. So the first axiom is um, closure property. Okay, I go through the axioms in page 161. So first, let's define this vector here. So um, oops, that's two, what happened? Okay, so let u equal, say, um, x1, y1, and v is x2, y2, and w is, say, x3, y3. Okay, so all these three vectors all belongs to the vector space. They all belongs to vector space V now. So now, vector V. So first is, let's say, a closure on the addition. So U plus V is x1, y1 plus x2, y2. And well, by definition, this is x1, y, x1, x2, okay, x1, x2, comma, y1, y2, uh, that belongs to vector because, well, this is a real number, right? These are all real numbers. So this is real number and the product of this real number. So real number, comma, real number belongs to, is an element of this vector. Now, number two is community property. So we know that u plus v is, we say, x1, x2, y1, y2, which is same as x2, x1, and y2, y1, which is, we can say this is, x2, y2 plus x1, y1, which is v plus u. So this is the second axiom satisfied. So third axiom is associative property. So if I say u plus uh, v plus w, well, I'm going to use u plus v plus w is, what is u? U is, I say, x1, y1 plus v is x2, y2 plus x3, y3, right? So that is x1, y1 plus, now here, this is x2, x3, comma, y2, y3, okay? So this is x1, y1 plus x2, x3, y2, y3 is, then I can now multiply x1, x2, x3, y1, y2, y3, isn't it? So this is same as x1, x2, x3, and then y1, y2, y3, isn't it? So which is x1, x2 y1, y2 plus x3, y3. But what is this one? This is x1, y1 plus x2, y2, isn't it? Plus x3, y3. So in turn, this is, u plus v plus w. So associative property satisfied. That's axiom 3. Now let's go to axiom 4. Axiom 4 is zero vector. What is a zero vector? In other words, if I say let u equal xy, then I'd like to have an additive identity. So it's obvious that x, y plus 1, 1, okay? This is element of a v, right? Okay, so which is x times 1, y times 1, which is xy. For the same reason, 1, 1 plus xy is 1 times x, 1 times y, which is xy. So from these two, 1, 1 is the additive identity for this vector v, okay, element of v, set v. I'm not saying vector space yet because we didn't prove yet. So now number 5, then 1, 1 is additive identity. So we should have 4 now. So to find u inverse, okay, need to show that x comma y, this is u plus u inverse is 1 comma 1. So x comma y plus now 1x 1y is x times 1 over x, y times 1 over y is 1 comma 1. So for every x comma y, the inverse seems to be, I don't know yet, seems to be 1 over x, 1 over y. However, 0 comma 0, which belongs to set V, does not have the inverse, since 1 over 0, 1 over 0 does not exist. Since 0, 0 does not have the inverse, axiom 5 fails. Okay, so it's not vector space now, but they say they want you to find all the axiom that fails. So let's check the rest of the axiom. Number 6. Number 6 is um, C number 6 is, let me check. Uh, Number CV. So C U is C x1 y1, which is cx1 cy1, well, which is, real number. This also real number. So that is an element of V, member of V. So 6 is okay. And check 7. So the one that fails is number 5 so far. And number 7 is what 7 says. C, oops. So C, it says U plus V is C x1 y1 plus x2 y2. Okay, what is this one? It is C x1 x2 and then y1 y2. But by the second definition of this is cx1 x2 cy1 y2. However, what is Cu plus Cv, which is C times x1 y1 plus C times x2 y2, which is cx1 cy1 plus cx2 cy2. Okay, but this is again by definition, isn't it? C square x1 x2 c square y1 y2. So we know that Cu plus V is not same as Cu plus Cv, because as you can see, this is, what is it? Cu plus V, whereas this is Cu plus Cv. They're not the same. This is C squared, this is C. So 7 axiom fails. Okay, so far we have 5 fails and 7 fails, right? And then axiom number 8. 8 is C plus D U, which is C plus D, C and D are constant, U is x1 and y1. Then by the second definition of this operation, he said C plus D x1 and then C plus D y1, which is, cx1 plus dx1 and then cy1 plus dy1. Then what is then cu plus tu? This is c x1 y1 plus dx2, well, same as x1 y1. There is no x2. There's only one vector we're talking about. Only one vector. It is u. So it is d x1 y1. So which is cx1 cy1 plus dx1 dy1. Isn't it cd x1 square, and then CD y1 square. So let's compare this one. So the first one is this, but CU du is that. Okay. So obviously they're not the same. So axiom 8 fails. Okay. And let's check the last two axiom, number 9. So axiom 9 is CDU, which is C dx1 y1, which is C dx1 dy1, which is simply C dx1 C dy1. Okay, which is C dx1, just real numbers, C and D, and then C dy1, which is C d outside x1 y1, which is CD. Well, I can put parentheses here, and CD, this is CDU. Okay. So 9 satisfied, 9 is okay. Or number 10 is simply 1 times U is 1 times x1, y1 is 1x1, 1y1 is x1, y1 is U. So 3 axiom 3 or 2, 3 axiom 5 and 7 and 8. So this is not a vector space. Since axiom 5 and what? 7 and 8. 7 and 8